Now we're recording. Okay, so, sent the textbook out to the publisher yesterday, and strangely they have not acknowledged receiving it, so I'm not sure what's up with that. So maybe it went to their spam folder. I don't know. So I just sent him an email asking, like, can you acknowledge getting this? As hard as I work. So I don't know. Okay, so based on questions that I've been getting about the homework, I'll try to have this awful board to deal with, and really green chalk. I would use it, except that colored chalk doesn't erase very well, and the board's already pretty bad shape as it is. So there's a few pointers for about Matlab use. There were some hiccups early on. Okay. So, although perhaps, hopefully everybody is up to speed on Matlab now since the first assignment is due today, but just in case. Okay. So first, so your actual code that you're using, and certainly code that you submit, should be in M files. So in other words, something .m, the extension, which could either be script M files, which would consist of commands that could be typed at the prompt, but by putting in the script file, you can run it several times. You'll not have to retype things. The whole process is much more efficient, and so then I can look at that and see what he did. For instance, these are often used to test your functions, and then function M files. For example, in this assignment, there's a solve diag.m. and so forth, and there were a couple other ones, like back sub was another one. So this that part of a file name, except for the extension, that really should match the function name. Well, now Matlab does not forbid you to mismatch, but I am because you're writing this function, function x equals solve diag whatever, and then the way Matlab accesses functions is by the file name, not what you put in the file, because it has to find it. It's going to find it by the file name. So those two names should be the same. So in general, for either kind of M file, now for scripts, you can call those whatever you want. And generally for homework problems, if I say you write a function to do this, I'm giving you the name of a function and its input parameters, so I'm laying it out for you. For a script M file to test these functions, I haven't specified what you call it, and I don't really care. But for M file names, you should limit names to letters, digits. I think an underscore is also allowed. It's like variable names in other programming languages, like C++. They call it an identifier, and also it cannot begin with a digit. So like C++, for example, allows letters, digits, underscores, and as long as it doesn't begin with a digit, then it's okay. And Matlab probably uses the same convention. I'm not sure what the rules are about underscores because I just don't use them. So I saw some file names that would have spaces or dashes or other special characters, not allowed. So make sure you keep that in mind so that you can actually run code. Because a function cannot be typed at the prompt. and it has to go in one of these files. Just like in C++, you would have your like .cpp files, and your code would go in there. It's a similar idea. Okay. I think of what else came up as far as Matlab issues.
I have a question.
Yeah.
What work are we doing on Matlab? I just got mine today.
Oh, I'm sorry. What was your question?
What's due? Is it something due today?
Well, yeah. So on the website is where I post the problems.
On your website?
Yeah, for the class.
Okay.
Yeah. So all the homework problems are listed there, and the problems themselves are in the textbook PDF. And most of those problems for this assignment, there are 6 problems altogether, involve MATLAB, or there's just answering a question about the code. Okay. Okay, so you just got MATLAB today?
Yeah.
Okay, all right. Okay. Yes, question?
I'm actually not sure what you mean by a command that can be typed at the prompt.
Oh, okay. In other words, what you would put in a script file are commands that, if you wanted to, you could type them at the prompt. It's just that you're streamlining your process by instead typing them in an M file, and then you're running the M file. So it basically simulates a session of typing things at the prompt. So
Okay, I think I know what that means.
yeah, and the main key thing is it would not include functions, not actual function definitions. That's really funny seeing you set the cat aside. But you would be calling functions.
So, ask, is it like when I am writing my homework, or when I did the last homework, I wrote a file that called all the functions.
Yeah,
so
that's
that was
script.
Like and I named it like Orlayla homework.
Yeah.
So you mean I could run that? I could like type the file name of my homework and have it run everything, and then it would run functions. So that's what you're referring to?
Yes.
Great. Thank you.
Okay. All right. And if you want, you can turn it in, because what I did last semester on one occasion was, since the assignment involved writing certain functions that had predetermined names, I wrote my own script that called everybody's functions, and so it helped. It was automated grading. It was kind of cool, except when the students wrote code that didn't conform to what it said in the problems, and I had to fix that. So keep it in mind, like when I in a problem, like write this function, make sure it conforms to those parameters. That way, I can just go ahead and run it, and I know what the result should be, and can take that into account. So it helps me grade your assignments more rapidly. Okay, so another point that came up, and so I'm trying to remember from anyone who's seen me lately to ask questions, like whatever issues came up. So if I'm forgetting something, feel free to remind me. So function file and files should only have a function in them. Like other commands and test function. That you put in a different file, like a script. So what I would suggest is, before you actually run your code, when you've got everything working and you want to run it, just make sure it works before you turn it in. So at the prompt, use the diary command. So for instance, you could do like diary homework1.txt, and then it'll log all commands that you use to run your homework and produce the result. Because if I could see in this file you sent me, like, oh, you ran this, it didn't have any errors, it produced a correct result, then it's very easy to just give you full points for it. And so then you can get a diary file and send that in as well. The M files are the most important thing. That's what I really need to see. Also, with a diary file, before you turn it in, you can edit this. in any text editor, like in Microsoft Notepad or text edit on a Mac. And the reason I point that out is some of these problems, if you don't involve writing code, but they're just a short answer thing. So if you want, you can just go ahead and type that in, like include it in your diary. So you're not having to make a separate document. You're not having to write it on paper and send me a picture, that sort of thing. I know that takes me to another thing, but I was trying to remember that I wanted to mention. Okay. All right. So. So when I said in class before, submitting one file, I only meant that for work done on paper. So that has nothing to do with your code. You're writing all these function files. You write them as separate files, and they should stay separate files when you submit them. It's easiest for me to run them that way if I want to do that. So I was only referring to not so much for this assignment, but later assignments. If I give problems that involve working something on a paper, like there are going to be some problems that are proofs. This isn't modern algebra, but still, that you that I prefer to have dumped into a Word document or made into a PDF or something like that, because it's a pain for my email reader to download a bunch of picture files, because they're all such high resolution, they're like a couple megs each, and I think USM's email server chokes on it, and it's just awful. So that's what I'm going to clarify that comment I made there. So what you could do is, what I recommend for when you're ready to submit it, you have all your files together, zip up all your files. If you have them in one folder, often you can do this on your Windows or a Mac, you can do a secondary or right click on the folder and it says compress, so it'll make a zip file out of your folder, and you can just send that. Then everything's in one place, and then I can just unpack it and grade it. So if you could do that, that would be appreciated. Okay. So any questions related to homework or its submission or anything like that? Okay. By the way, the second homework is on the site, so that'll be due a week from today. So it's on the section I'm finishing today, and the second quiz it was just put up in Canvas, and you have until Friday to do that. So after today's class, you'll have all the information needed for that. I will always have the Canvas quiz due first, because you guys, the quiz is meant for you to understand at least the terms of a section, and which you would need to be familiar with to do the other problems. So, also, one thing that I want to point out, this is something that came up last semester as well when I was doing the quizzes. I can understand wanting to get the quiz over with quickly by looking for the correct portion of the text to supply as the answer, but it is important that you at least still be examining the whole section, because sometimes the answer that I get misses a mark, in that whatever's said may not be incorrect, but it's not the portion that's actually addressing the question. So please keep in mind, these are reading quizzes, so the time should be taken to actually read through the section and then try to adjust what's there. Okay, so are there any questions about the homework problems themselves?
Pretty straightforward.
Okay. Well, especially, I would imagine more so for grad students. Speaking of which, since we have a, last semester was different because we had it was all undergrads. Now we have about equally balanced between undergrad and grad students. So what I will do, and I'll figure out the details of it, especially once I see how things flesh out, is because I've been assigning the same work, that I will apply a curve of some kind to the undergrads, because I would expect the grad students to do better. So, yeah. So, and I guess for the undergrad especially, maybe we'll save some. And we're not talking some huge curve. I think I've done 10 points in the past, but we'll see. I think that would be particularly important for the tests. Okay, so that's the last chance for now for any homework questions. Or
One last thing for those of us that misunderstood the one file.
Yeah. Oh, okay.
Can we send you a zip file afterwards?
Oh yeah. I haven't actually looked at any submissions that I've gotten. I just filed them in my to grade folder, so I don't. So what happened in your case?
Oh, I heard one file and as always submitted it in a nice latex form.
Like you did last semester?
Oh, yeah.
Oh, I see. Okay. Yeah, it'd be good to have the actual M files broken out so that I could just save them and run them.
Yeah, okay.
Yeah. I may not necessarily run the code. I'm basically going to determine what is going to be the easiest way to determine if what you did is correct. Because sometimes it's easier for me to just look at the code, and that might well be the case here because the algorithms are fairly short. But okay. All right. So yeah, if you feel the need to redo what you've submitted, you can certainly do that, especially since the due date hasn't hit yet.
Is it due at midnight or is it before?
Oh.
8 in the morning? Because I didn't pass to do that. So.
Oh. Okay. Yeah, I'll stick with that because I'm not exactly going to be rushing to grade these things.
Mm-hmm.
So, okay, I will try to do them expediently.
Yeah.
Because otherwise assignments are going to pile up and that's going to be bad. But yeah, okay. Well, let's just set a specific time because whenever I get here, it tends to vary. Okay. Well, let's just say 9 a.m.
Okay.
That's
The next day?
right.
Right.
Okay. Yeah. But yeah, one thing that drove me nuts is tomorrow I have my own deadline to submit something for a conference, but the conference takes place in London, so we set the deadline for midnight London time, or Greenwich Mean Time.
Oh, so about now.
So it's a good thing I looked at the deadline because I thought, it's sometime mid-February. It's like, oh no, it's tomorrow. And yeah, so that's 6 p.m. here. So midnight doesn't always mean midnight. So, dang it. Okay. So, all right. So now what I'm ready to do is finish up this section. So last time I covered how Gaussian elimination is equivalent to the LU decomposition, but the LU decomposition doesn't fully address everything we need. And yes, I am still kind of winging this, just because I don't like looking through notes to see what am I supposed to cover. But I have a textbook open in case I really need it and forget something. But okay, it's laptop moving time. Okay, well, thank you for leaving plenty of room in between you guys. Okay.
Can we just get it back?
Oh, yes. Yeah. Okay, I'll hold that. Okay. Wouldn't have to buy you a new laptop. Okay. All right. good. Alright. I guess I'll have to touch this every now and then to make sure it doesn't fade. Okay. That's good? Okay. Did you mute yourself? Oh, okay.
Yeah, sorry.
Alright.
Oh, just a little bit more.
Okay.
Stuff. Good,
Okay.
perfect.
Alright. Of course, once I move it back and then move it again, I'm not going to remember that. But okay. So as a quick, let's see how much time I've wasted. Okay. So recap is to solve a system X equals B. This chalk seems really light.
There is.
Yeah. Wait. Okay. Let's see if this is any better. Is that better?
Yeah,
No.
modestly.
Or maybe it's the board.
I think it's the board.
Maybe erase it. Did you go back over with your erasing?
Yeah, I think it's better. Dang it. Okay, maybe that'll help.
Yeah.
Okay. It's like we do double erasing every time. Ugh. I have to talk to whoever has class in here before. Like, what are you doing? It's not erasing. Okay. Okay, so those in the back, that says recap to solve AX equals B. The first step is Gaussian elimination, which produces LU decomposition. A is equal to LU, where L is lower triangular, U is upper triangular, hence the L and the U. And what goes in the L, what is in the L?
Well, the L, that's the inverse of the multipliers.
Yeah, so the matrix is used to do row operations, but L itself actually contains, yes, the multipliers. Mij, so we basically have a record of row operations. And then the matrix U is your row echelon form. In other words, it's a result of Gaussian elimination. So you do the reducing to get it to upper triangular form, and there it is. And this requires order n cubed flops, floating point operations, or arithmetic operations. Okay, so that's the expensive part. And then you do. The thing is, that is only applying the row operations to A. You still have to apply them to B, and forward substitution does that. And so the net effect is you're solving Ly is equal to B. So Y is so B is your original right-hand side of your system. Y is the results of your row operations on B, and this is a lot less expensive, so it takes n squared minus n floating point operations. And then finally, what's the last stage called? Back substitution. I think for consistency we should call it backward substitution, but for some reason they call it back substitution. I guess because it would make no sense to call it for substitution or whatever. Okay, back substitution, and then you're solving Ux is equal to Y, because if you multiply both sides of that by L, you get Lux, which is Ax, and you get Ly, which is B. And that takes n squared flops. Actually, I can be a little more specific about this. It's roughly 2/3 n cubed floating point operations, and that 2/3 is going to be important later on in this chapter. That's why I'll mention it now. Okay, so it seems like, well, when it comes to solving system linear equations, we're done, but we're not, because we're actually going to spend a lot more time on solving systems of equations, because there are some issues with this approach. And the issue that I'm going to focus on today is, okay, so let's section it off here. All right, so what can go wrong with this approach? And it turns out that, because here we're relying on the matrix A having this LU decomposition, but this decomposition does not always exist. Okay. So in fact, I can go ahead, well, I do have an example in the book, but also I could just make one up. Example of a small, simple matrix for which the LU decomposition doesn't exist. I want to make sure that both laptops can see the far right edge of a board. So you can tell me when to, okay. All right. To get much easier than I thought. Now, so as an example, let's let A be equal to okay. So if we go ahead and start performing Gaussian elimination, right now there isn't anything about this matrix that make you think that something's going to go wrong. Seems okay. So, so what happens is you start carrying out row operations to eliminate these entries in the first column. So now I've chosen this example to make it really convenient. That by putting a 1 in that 1, 1 position, the multipliers are going to be nice numbers, integers. So your first multiplier is going to be the -2 that you want to get rid of, divided by the diagonal entry in the same column. So it's just going to be -2. And then your other multiplier is going to be that second entry you want to eliminate, that 9, also divided by 1. So that multiplier is 9. So when you carry out these row operations, so I'm going to take -2 times the first row, so that would be -2, 4, -6, and subtract it from the second row. So we have 0, 0, and then 7 minus 1 minus 6 is 13. And yes, this is unlucky indeed. That part I didn't plan. And then 9 times the first row, so 9 minus 18 and 27. So we have 0, 8 plus 18 is 26, and 2 plus 27 minus 25. Okay, so if we want to carry out Gaussian elimination, why is it that we cannot?
0.
Because that's 0, because my next multiplier, I want to get rid of this entry. So multiplier 3,2 is supposed to be A32 over A22, and we'd be dividing by 0. So this matrix A does not have an LU decomposition. So what's the really easy way to fix this so we can continue? We just go ahead and switch for rows. And it's something that you would have learned about in your first linear algebra course, your 326. That's one of the elementary row operations is switching rows. But it turns out when it's the computer doing the work, there's one reason why, in 326 land, it was the only reason you'd ever have to switch rows. But it turns out when it's computer doing all the computation, instead of doing it by hand, there's another very important reason to have to swap rows. And this is called pivoting. So what I'm going to do is, so first, I want to nail down the whole question of existence and uniqueness of the LU decomposition. Since I was one of the quiz questions. Okay, and back we go. Should probably write more on the board each time. Not have to do this as many times, but I don't like to use a small font. Okay, let's see. All right, is this a good view? Okay. So this decomposition, A equals LU, exists if and only if, actually need to give some notation first. The determinant of these matrices, AK, is non-zero, where AK, I describe it two ways. First, using a Matlab-like syntax, and then I'll draw a diagram. It's rows and columns 1 through K. So in other words, if I were to write out A, actually I'll just use the example from before. 7, 8, 2. Okay, so the first 1 by 1 entry by itself, that's A1. Then the upper left 2 by 2 block is A2, and then the next one would be A3. So each AK consists of the upper left K by K submatrix. So you're going to have n of these, so in this case A3 is a whole matrix. So not only do you need A to be non-singular or invertible by having a non-zero determinant, you need all of those submatrices also to have a non-zero determinant. Now that's kind of a pain to check. In fact, the process of checking that is as expensive as Gaussian elimination itself, so we're not really going to do that. Instead, we're just going to interchange rows as needed, because as long as a matrix is invertible at all, there will be a way to interchange rows so that Gaussian elimination can complete. If it's not invertible, then what are we even doing? We're not able to solve the system at all. Okay, so this is a question of existence. And then, if the LU decomposition exists, it is unique. And since I did not assign the problem, I don't think I did. Maybe I should check that. Come on. Okay. Oh, yeah, I did. I did not assign the problem of proving that it's unique. So I'll just go ahead and show you. So I'm going to prove this by contradiction. So I'm going to assume A has 2 LU decompositions, L1U1 and L2U2. And we'll assume that these are distinct. Now, L and U, both these L's and U's, they're all invertible. So I can multiply by their inverses and rearrange. So for instance, I can multiply on the left by L1 inverse. And I can also multiply on the right by U2 inverse. Now, on the left, we have an upper triangular matrix and the inverse of another upper triangular matrix. Last time we talked about properties of upper and lower triangular matrices. So what type of matrix do we have on the left side? Like for instance, if I take the inverse of an upper triangular, what do I have? Right? And if I multiply them? Yeah. So I have upper triangular on the left. What do I have on the right?
Lower.
It's the same idea. Lower triangular. Now, what more do I know about the right? Besides the fact it's lower triangular, what else do I... Because it's not just any lower triangular matrix. What's the subtype of lower triangular matrices we saw?
Diagonal.
What? Not that. Well, we'll kind of come to diagonal later, but... Unit, what does that mean?
All ones on the diagonal.
All ones on the diagonal. So, L1 and L2 are both unit lower triangular. So, using my crazy shorthand from last time, so is that. So, what happens if you have a matrix that is both upper and lower triangular? What? Well, we're getting there, but that alone we don't know from this alone. But anyone else?
It's a diagonal.
Diagonal matrix. Yeah, because this says the lower triangle entries must be 0. This says the upper ones must be 0. They both must be 0, but diagonal is all that's left. But a unit lower triangular matrix that is diagonal is the identity. Yeah, because we already said all the diagonal entries must be 1. So just from triangularity alone, we see it must be a diagonal matrix, but because it's unit, it is identity. And now if we apply that over here, what does that mean? That, so for instance, L1 inverse L2 is identity. Now I can multiply both sides by L1 on the left, and I get L2 equals L1. And similarly, I could say, well, this is identity, therefore U1 equals U2. So this is a contradiction. We said these. I assumed up front that these LU decompositions are distinct. Well, no, they must be equal. Therefore, the LU decomposition is unique. And this is how pretty much any uniqueness proof ever goes. You assume there are 2 of them, whatever it is, and you arrive at a contradiction based on whatever properties that might have. So those of you who have proof-intensive classes ahead of you, keep that in mind. Okay, so any questions about what happened here with LU? All right, so now that we know it doesn't exist, we know we need row interchanges, but I need to describe what is the other issue with that leads us to have to do row interchanges in the first place. Okay, Layla, I want to make sure that you can see the midpoint of a board, like this divider. Okay, all right. Okay.
Sorry, no, I can't see it.
Oh, you just didn't.
I was saying, oh yeah, I get what you mean by the midpoint of the board
Okay.
now. That's fine. I was nodding.
Now?
Keep going. Go, 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 go. There.
Okay. All right. So, all right, so why row interchanges? First, reason I already gave is to avoid dividing by 0. And even if it's not exactly 0, if it's almost 0, that would could be a problem. All right, and the second reason has to do with round-off error. In other words, the error that is inherent in any computer arithmetic operation or floating point arithmetic operation. So to explain what I mean by that, I'm going to focus on the main step of Gaussian elimination, where you're performing a row operation and carrying this out like in the innermost loop. Okay. Because what's happening is, during Gaussian elimination, you are continually overwriting entries of a matrix. You're always updating them as these row operations are performed. So entry like this AIK or AJK might be overwritten with a new value several times, especially if a matrix is large. So this value here is, unless you're just starting, is already contaminated by round-off error as a result of previous operations. Okay. But then what happens with this AJK value? Now we're multiplying it by the multiplier. So the problem is, what if this multiplier value is large? Why is that a bad thing?
It's going to compound the error.
Yeah. So whatever, if we think of this AJK, if I write it as I'll put a hat here to indicate like the exact value plus some epsilon, which refers to error. And okay, so this is exact. So what happens is, it's just a matter of distributive property, that both the exact value and the error are amplified by Mij. So now, what that means is AIK is even more erroneous than AJK is. So if you have large multipliers, that error is just going to grow. It's just going to throw off everything more and more. So this is one reason, a secondary reason why we perform row interchanges, and more often than you would need to if you're working this out by hand, to try to rein in that propagation of round-off error. Okay. So the solution we refer to as pivoting. So now what I'm going to do is describe a couple approaches, and there are many different approaches to pivoting. I'll just describe the most basic two. Okay. And here we go again. Okay. Right. You see this far? Okay. Yes? Okay. I couldn't tell if it was a thumbs up or something else. Okay. So pivoting strategies. Most commonly used is called partial pivoting. And the thing is, there's partial pivoting and there's complete pivoting. When I describe partial pivoting, there will be nothing about it that will indicate why it's called partial until I describe complete. So the idea behind partial pivoting is just realized that I think when a piece of chalk is longer, my writing ends up being naturally lighter. Okay. But then one time, I think it was in class, maybe it was last spring or so, yeah, where I dropped a piece of chalk and it fell to the floor and broke in two. And I just said, well, I guess that makes me 2/7 of a Jedi. And there weren't many people in the room who got it. And apparently, hardly anyone here who did either. So, never mind. Okay. So before eliminating entries, in column J, so in other words, you're about to start doing that. You want to find a row P where P is between J and N. So you're going to start from the diagonal and search all the way to the bottom. So that the entry in row P, column J, in absolute value is equal to the maximum of all of those entries. Okay.
What's the first line in front of column?
In column J?
Yeah.
Okay, so in other words, so you're starting at the diagonal, looking all the way from there, below it to the bottom, you're finding out, of all those entries, which entry is the largest in magnitude. And once you do, you're going to swap rows P and J. And then you're going to continue with Gaussian elimination like before, and then when you move to the next column, you're going to check that again, and so on. Actually, I'll just write that out. Rows P and J. So I'll make up an example. Okay. Let's see. So. Okay, so before you start eliminating entries in the first column, you're going to look at, in this case, the entire first column, and you're going to find the entry that's the largest, and that's the 7. So now you're going to interchange rows 1 and 2. So you have 7 minus 3 and 6, 2, 1, 2, 5, 4, 3. Okay, and now you'll proceed with Gaussian elimination. So the multiplier for a 2, 1 entry is going to be 2 over 7, and then what's the multiplier for entry 3, 1? Because we're going to eliminate these.
5 over 7.
5 over 7. Right. Okay. So now when you carry that out. Of course, arithmetic-wise, it's going to be a pain. Okay, so, well, we know what most of the entries are going to be. Okay, so then it's going to be 1 plus 1 plus 6 sevenths. So that's going to be 13 over 7. And then I have 4 plus 15 over 7, so that's 43 over 7. Okay, and then I have 2 minus 12 over 7. So that's going to be 2 over 7. And then, okay, so then 3 minus 30 over 7. So minus 9 over 7. Okay. So now, the first column is done. We move to the second column. And can anyone tell me if a row interchange is going to be needed this time?
You want the biggest on top?
Yes.
Then yes.
Yeah, and by on top, it's here, the diagonal entry. Yeah, you're only going to search this portion of the column. This part's done. And yeah, so in that column, 43 over 7 is the largest. So you're going to swap again. And so 0, 43 over 7, 2 sevens, and 0, and then 13 over 7. Whoops. I got to swap the entire row, not just that column. Okay. And now I'm going to target this entry for elimination. I'm not going to actually carry out, but I do want you to tell me I'm eliminating entry 3, 2, row 3, column 2. So what's the multiplier going to be in that case? What? Sorry, I couldn't hear. 13 over 43. Okay. All right, and then you would carry the row operation, then the matrix would be over triangular, and then you're done. Okay. Now, let's take a look at the multipliers. And also, it'd be a good idea to look at the previous example I did when I was showing that LU didn't exist in that case. I did a couple row operations. If you compare these multipliers to the multipliers from that earlier example, where my diagonal entry was just 1, so I had like a 2 and 7 or something like that. What do we notice about these multipliers?
They're more difficult.
What?
They're smaller.
Yes, and that's the whole idea. Because by making sure that your denominator in your multiplier is the largest entry that you're considering, the effect is that the absolute value of any multiplier is less than or equal to 1. So it's going to contain that propagation of Raulever. Propagation will still happen, it's just not going to mushroom on you. Although, I want to point out, even though now the entries of L are going to be controlled in magnitude, because also the diagonal entry is equal to 1, U can still grow. Those entries can still get large, and that also is going to be a problem later on for like back substitution. But at least this helps compared to what we had before. And there's actually a homework problem, or second homework, that highlights just how bad it can get for growth of entries in U anyway. Okay. Now, as far as the work is concerned, because now we have extra work to do. We have to find this largest entry. So now it doesn't involve any arithmetic. What it involves is comparison. Well, that still involves some overhead. It's still something a computer has to carry out.
Yeah.
So still examining every bit of these floating point numbers. So, so the extra work involved is a certain number of comparisons. So we talk about the complexity of algorithms like forward back substitution or order n squared, and Gaussian Elimination order n cubed. What's it going to be for me doing the comparisons? Order n to the what? Because if you think about how many comparisons I had to do in each column, it's less as you go, but then you're having to add all that up. Because I have to compare, I have to examine each entry, like every entry in the first column, almost every entry in the second column, and then decreasing from there. But all of that together is order n to the what elements to examine.
It's gonna be like 3 plus 2 plus 1. Right.
Not factorial. Okay, let's go with that. So in other words, in general, n minus 1, n minus 2, etc. So like if you're summing the numbers from 1 to
A
n,
summation of them.
which is,
A summation of n.
right, but the formula for that, right?
N minus 1 squared over n minus 1.
Warmer,
It's some m plus 1 squared over m plus 1.
You're throwing too many exponents in there. Anybody?
M plus 1 over m. Just gonna keep throwing stuff out.
Now it's just math salad. So.
I know.
Well, what? Oh, you.
No, it's wrong.
Okay. Oh, no, sorry. What did you say? It is n squared.
Yeah.
Okay. Well, also, if you were looking up in the book, then it better be right.
My computer's listed.
Oh, okay, all right. Yeah, because if you figure n minus 1, n minus 2, so summing all the numbers from 1 to n, the formula is n times n plus 1 over 2.
Yeah.
Okay.
Dang.
All right, which is order n squared. Now, how come this is not a big deal?
Because that's not a big amount.
Right, not as big amount as what?
Into the third.
Yeah, but the amount of work we're already doing
Yeah.
for Gaussian elimination,
Right.
especially when n is large, this is negligible compared to that. So this is the most common method that is used. Okay, now how are we doing on time? Oh, geez. Okay, now. I'm going to address very quickly the other approach that's commonly used. Okay. So, complete pivoting, which might be everyone's called partial. You swap rows and columns. In other words, not only rearranging the order of the equations in your system, you're also rearranging the order of the unknowns. So swapping rows and columns to make AJJ equal to the maximum over all indices P and Q between J and N. So you're searching the whole part of the matrix below and to the right. So you're looking for the largest entry in that whole block. So then you swap rows P and J and columns Q and J. Whichever P and Q you find the largest one in, you do that swap. I realize my notation here is actually incredibly sloppy. Actually, I'm going to fix it. Okay. Okay, now it's correct. So I'm still searching all indices from J to N. And then once I find the largest ones, then I swap those rows and those columns. And that will reduce the size of the multipliers even further, and also limits the growth in entries of U. It turns out they don't know by how much. It's never been proven that, like for partial pivoting, it's known how large the entries of U can get. We don't know for complete pivoting. There's been some speculation and conjectures proven false and so forth. But the point is, it's a better situation. So this is more effective at containing round-off error. But what about the cost? You're searching more of a matrix for an entry to swap with. So for instance, when you're dealing with the first column, you're searching the whole matrix, all n squared entries. Then you're searching like n minus 1 squared entries and n minus 2 squared. So you're adding up a bunch of squares, which gives us what for a total cost of comparisons? Anybody take a stab at it?
N cubed.
N cubed.
Wow.
Yeah, it's worse. That's the key than partial pivoting, because if you, it comes from this summation formula that was seen in discrete. Sum of first n squared is n times n plus 1 plus 2n plus 1 over 6, which is order n cubed. Okay, so now that work done just to do the swapping is on a par with the work of Gaussian elimination itself. So people don't normally do this, but it's still out there. So it's still we're covering. But general purpose software tends to include Gaussian elimination of partial pivoting, even though it can perform poorly in some cases. For most part, it's effective enough for a general system that people are happy with it. Okay, so there are other pivoting strategies in this, but these are the main two. So any questions about either of these?
What is the PQ on the first A supposed to be?
Oh, here?
Yes.
Okay, I'm saying, so PQ ends up being the actual entry that ends up being the largest of all that are searched. So for instance, we search the whole matrix, we find that entry A43 is the largest, then P is 4 and Q is 3, and we would swap rows 1 and 4 and columns 1 and 3. Okay. All right. Now, during the remainder of the time, you explain back to partial pivoting, so only swapping rows. How does this affect the process of solving AX equals B that we're already doing Gaussian elimination and forward and back substitution? So how does this affect the LU decomposition? Well, what's happened, for the example from before, I started with A, and I'm trying to reduce it to upper triangular form. So what do? I multiply by P1, which is called a permutation matrix. And I'll explain what it is in a moment. That carries out for row swap. So just as other row operations can be viewed as a matrix multiplication, so can row interchanges. And then I do the row operations. Actually, I'm going to use a superscript here just for consistency. So row operation, then elimination. Then I move to the second column. Swap rows again. And then do an elimination. So it goes back and forth like this. And now for the 3x3 example, this is all I would have to do. But in general, I would keep going all the way to column n minus 1. And I get U. But the problem is, because I'm alternating these, it doesn't really, it's not conducive to having a clean factorization where I have lower triangular times upper triangular. Because remember, L is made up of the inverses of these guys. But now they have permutation matrices in between. So how am I supposed to get an L from all of these? And the answer is, I'm actually not. Not these as is. What I need to do is, we swap the multipliers too. So now what I mean by that is, okay. All right. When you're carrying out Gaussian elimination, and you're trying to reduce it to upper triangular form, and you see, oh, you need to do a row interchange. Well, of course you have to do row interchange on the part of a matrix you're actually operating on, like where you're updating elements. But what are you doing? You're storing the multipliers in your lower triangle. So what if you? So if you store the multipliers in that lower triangle as you go, and actually one of the homework 2 problems requires you to do this, when you see, oh, you got to do a row interchange, swap that part of a row too. In other words, you swap the entire row. Okay. And the result of that is the following. That you get your U by performing all of the row interchanges. I know I need to illustrate permutation matrices. I will in a second. You do all the row interchanges up front, and then you have different matrices. I'll call them M1 tilde, M2 tilde. That carry out the elimination. And the relationship between these and these is you're swapping rows and columns. You want to maintain that unit lower triangular form, but now you're rearranging the orders of the multipliers. This is fleshed out more in the book to explain why this actually works. There's an example there, but unfortunately I don't have time for now. But now this right here, just like before, is L inverse. So the new factorization is PA is equal to LU. So A may not have a it might not have an LU decomposition, but PA does. Now permutation matrix all you do to get one is you swap the rows of the identity matrix. So for example, P equals like 1 0 0 0 0 0 0 0 1 0 1 0 0 1 0 0. What I've done is you swap rows 2 and 4. So multiplying on the left by a matrix like that will swap rows 2 and 4. So it's another elementary row matrix. And P inverse is equal to P transpose. So it's very easy to invert a matrix like this. You're basically undoing the permutation. So this is what's called an orthogonal matrix. It means the rows and columns are orthonormal vectors. And this is actually used to rearrange this factorization. So instead of this alternating pattern, we get something like this. So that's the basic idea behind a permutation matrix. And I admit I'm rushing because I'm almost out of time. But so the last point I want to make, and maybe I'll do some cleanup on this at the start of class on Thursday, is now that what are you doing to solve AX equals B? Now that you have this slightly different decomposition, and fortunately it'll be very quick to explain that. Okay, so all right, so what you do is you do Gaussian elimination with partial pivoting, so you're only interchanging rows, not columns. And that gives you this decomposition. PA is equal to LU. So what you do is, to have a record of the row interchanges, what you do is you swap rows of, if you have a vector that has all the indices 1 to n, anytime you swap rows of A, swap rows of this index vector also. I can talk more about the Matlab implementation of this on Thursday, but so don't store the matrix P. That's a waste. Most of the entries are 0. So you can store a vector that indicates here's how the rows were rearranged. And then your A holds U in the upper triangle, and then all the multipliers in the lower triangle, like before. And then you do forward substitution to solve Ly is equal to PB. And you can see that by multiplying both sides of Ax equals B on the left by P. Because if you're swapping rows of A, you have to swap rows of B as well. You're applying all the row operations to B and A. And then you do back substitution. That part is no different. You're solving U times X is equal to Y. So this is it. This is how you solve Ax equals B in a general case using a direct method that's the subject of this chapter. And one of the functions that you'll write for homework 2 is a function that actually carries out all of this. But from homework 1, you will have a back substitution function. You will also have a Gaussian elimination function that will be worked on during homework 2. And so your function to solve Ax equals B is really just delegating. It will call a function to do this. It will call another function to do this, and another to do this. So it has very little work to do itself. It's passing a buck. So this is how these applications are built, is that you're breaking them down to manageable pieces and making sure that each piece does its job and then putting them together in the right way. Okay. Dang it, I've got 1 minute past time. So what I will do is, to help you guys with homework 2, I will discuss at the beginning class on Thursday what is involved in carrying this out in Matlab as far as swapping rows, easily doing B rearranged also. Matlab makes it very easy to do those things, but I need to show you how. So I'll save that for Thursday. So great. I'm behind a little bit. Yay. Okay. Okay.